Hello students, uh, today we are going to start a complex number second part, that is from page number 55, 2.4 properties of complex number. That means we are going to learn about properties of complex number. Uh, Properties of complex number 2.4. So you can see in the book page number 55. So first is properties of complex number, that is so far the students are familiar with the algebraic operations of complex numbers. Now in this article we will discuss some properties of complex numbers. So if we don't know the properties of complex number, we will get difficulties in future to do the sums of complex numbers. So first of all, we must know the properties of complex numbers. So first property is that if a plus ib equals to 0, then a equals to 0, b equals to 0. It means a plus ib is equal to 0. Here it is given then a is equal to 0, b is also equal to 0. It means that the sum of this and this is 0. So both may be 0, or either a will be 0 or b will be 0, or a and b both will be 0, or this one minus 1 plus 1. When we do calculation, one is positive, same number, one is positive, other one is negative, we get 0. So here it is complex number, so we don't do that. This is related to algebra, so this we don't do. So here if this is 0, this is also 0, then only we will get addition is 0. This will like this, 0 plus 0i equals to 0. A plus ib equals to 0. That means 0 plus 0i equals to 0. In place of a, what is there? 0. In place of b, what is there? 0. So a equals to 0, b equals to 0. So this is the property. First property of complex number for addition and subtraction and all. This is for addition. A plus ib equals to 0. Then a equals to 0, b equals to 0. Since a plus ib equals to 0, so we have a equals to minus ib. So it is showing, this one is just what I have shown just now. This is just example. Now in exam, if it comes that if a plus ib equals to 0, then show that a equals to 0, b equals to 0. Then we have to start the sum from here. If it comes in exam to prove, how do you do? A plus ib equals to 0, a equals to minus ib, then we will do squaring both sides, then what do we get? A square equals to, minus square is plus. See here, always be careful, otherwise we do the mistake. I square is minus 1, we directly put minus square is plus, but I square is minus 1. So minus b square. Let me show you again. I b whole square. Let me write separately. Minus 1 square into I square into b square. Meaning of this, only minus sign is there, means we can write minus 1. I b, there is square. So I have written three terms separately. So minus 1 square is 1. I square is minus 1. B square is b square. So minus b square I have written here. I hope you understand. So a square minus b square comes this side. B square equals to 0. A square plus b square equals to 0. Here a and b are reals, and so a square and b square are positive. Therefore their sum will be always 0. If a square plus b square equals to 0, then a square or b square both must be 0, otherwise it is impossible. The sum of two numbers will be 0 because both are positive. A and b both are positive. If it is minus a plus a, even it is negative a square. Negative number, if we do square, we get always positive. So a square will be 0, b square will be 0. A square if it is 0, a also 0. B square if it is 0, then b also 0. So hence proved. This is the first property. This is very easy. Here there is nothing to understand. Just go on doing, you will get automatically. There is nothing to understand. So this is property number 1. It may come in exam to prove. So this is the procedure to prove the sum. Next, equality of complex numbers. Equality of complex number, what is the meaning? The meaning is that real and imaginary part there are two complex number. Let me write, one is a plus ib, this is a complex number, equals to another one, that is c plus id. So in this case, if it is equal, then real part and real part will be equal, and imaginary part and imaginary equal. That is what next property, equality of complex numbers. Two complex numbers are equal if and only if the real and the imaginary parts of one are respectively equal to real and imaginary parts of other. Real part of this side equals to real part of this side. If there is equal sign, then only imaginary part of this side will be always equal to imaginary part of this side. Let me show you one more example. 5 plus 3i equals to x plus iy. So both are complex numbers. So directly we can write x equals to 5, y equals to 3. Real part equal, imaginary part equal, because there is equal sign. This is second property. Both sides, if there are two complex numbers, then real part of left side is equal to real part of right side. Imaginary part, this is imaginary part because I is there. Here there is no I, so it is called a real part. Here there is I, this is imaginary part. There is no I, this is a real part. So this is imaginary part and this is imaginary part. So real part will be equal to real part, imaginary part will be equal to imaginary part. So this much you have to learn. So here it is showed, how it is showed, two complex numbers are taken, Z1 and Z2. So why Z1? Now when we do algebra, then we take, suppose the sum of two digit is 5, then we take one is, let one digit be x. So in general maths, while doing equation, we generally use the letter x, but in complex number we use the letter z. Already I explained in previous video that z is denoted for complex number. So if we want, we have to take two or more complex numbers, then we will use z1, z2, z3 like this. If only one complex number, then we will use z. If it is more than one complex numbers, then we will use z1, z2, z3, z4 like that. But we will use the letter generally z for complex number. So this proof I will show you here so that you can understand. Taken two complex number, one is a plus ib, other one is z2 c plus id. What is the theorem? That if two complex numbers are equal to each other, real part equal, imaginary part equal. According to condition, z1 will be equal to z2. Two complex numbers are equal, so I have written z1 equals to z2. If and only if the real and imaginary parts are respectively equal to the real and imaginary parts of the other. So z1 means what? A plus ib equals z2 is C plus I D. A minus C equals to I D minus I B. A minus C equals to I D minus B. A minus C minus I D minus B equal to 0. Sorry, something there is mistake, I think. B minus D. Okay. A minus C plus I B minus D. I hope you understand this one. Minus I D plus I into D minus D is minus ID. If we multiply this one and this one, and if we multiply this one and this one, you will get same thing. Only I have changed the sign. A minus C plus I B minus D. Here minus I means multiply. Minus I into D, I minus D. Minus I into minus B plus IB. So just change, interchange. A plus A minus C, IB equal to 0. Now, look here. Let me write this way. No problem. There is no issue. 0 is written, 0 plus 0 I written, same thing. Or if we write I comma I dot 0, then also same thing. 0 plus I 0 or 0 plus 0 I, same thing, is not it? So this one and this one equal. Now left hand side real, imaginary. Right hand side real, imaginary. So according to condition, we write this way, equating real and imaginary part we get what do we get? A minus C equals to 0. Real part, what do you get? B minus D equals to also 0. I cancel. B minus D equals to 0. B minus D equals to 0. Here what do we get? A equals to C. Here what do we get? B equals to D. We have got A equals to C, B equal to D. That means real part and real part equal. We have proved. Imaginary part and imaginary part equal. We have proved. This is what we have to do if it comes in exam. Otherwise, you have to apply this theorem in different sums of the exercise. Closure property. Now, closure property of complex number. Forget about complex number now. Now, closure property of any other number, simple number. Suppose integers. If we add any two integers, then we will get the result also integers. Any integers, minus 5, minus 4, minus 3, 1, 5, 6, 100, any, all are integers, 0, all are integers. Any integers if you add or subtract, you will get again integers only. So that is called closure property. If we don't get, that is not called close, means close to integers. For example, minus 4 plus 6, how much? 2. Minus 6 plus 4, how much? Minus 2. Both belongs to integer. So it is closure property. So closure property in addition, closure property in subtract. If we subtract, then also we will get what is called integer. But for natural number, let us see it is closure or not. Natural number subtraction. In subtraction, it is closure or not. 5 minus 2 equals to 3. It belongs to natural number. But 2 minus 5 equals to minus 3. It does not belongs to natural number. So in subtraction, closure property does not exist. So this is called closure property. So this is example what I have showed you, so that you can understand what is the meaning of closure property. It is already shown in article 3 that Z1 and Z2 are complex numbers. Z1 plus Z2, Z1 minus Z2, Z1 into Z2 are again complex numbers. then Z1 by Z2 is also complex number. That means Z1 and Z2, two complex number. As I have told you already in previous sum. In previous sum, we have taken Z1 and Z2, two complex numbers. So here also Z1 and Z2, two complex number, maybe A plus IB, maybe C plus IB, whatever. If we add, if we subtract, if we multiply, if we divide, then also we will get complex number. We will get complex number. But in this case, Z2 should not be equal to 0. Because if we get 0 in denominator, that is meaningless. So what do we understand? Addition, subtraction, multiplication and division. If we do for any complex number, we will get the result also complex number. It means that complex number shows closure property. So I hope you understand that. Closure property already you got in different chapter. But this closure property is for complex number. The system is same. Commutative property. 5 plus 2 equals to 2 plus 5. 5 into 2 equals to 2 into 5. It is closure property of addition and multiplication of natural numbers. Commutative property of addition for natural number. Commutative property for multiplication for natural number. Any two natural number, if we add and if you alter the number, also we will get the same result. 5 plus 2 is 7, 2 plus 5 is 7. 5 into 2 is 10, 2 into 5 is 10. When for addition and for multiplication, commutative property exists for what? For natural number. Now it is complex number. Same thing. If we add Z1 plus Z2 and if we add Z2 plus Z1, we will get same result like this. 5 plus 2 and 2 plus 5. If we multiply Z1 and Z2 and if we multiply Z2 into Z1, then also we will get like this same result. So commutative property with respect to addition, commutative property with respect to multiplication. I hope you understand. It is very easy actually. Now associative property. I will show you one example. 2 plus 3 plus 5. 2 plus 3 plus 5. Whether I put bracket here or here, result will be same. No? Similarly, multiplication also. 2 into 3 into 5. 2 into 3 into 5. Whether I put bracket here or here, result will be same. Same thing here also, which is called associative property. So I hope you understand. Z1 plus Z2 plus Z3. Three complex number. Putting bracket here or here, same thing. Then similarly same, Z1, Z2, Z3. Z1, Z2, Z3. Wherever you put bracket. So for associativity shows with respect to addition for complex numbers. Associativity shows with respect to multiplication for complex numbers. Then distributive property. This one also I will show you one example. 5, 2 plus 3. No, 5 into 2 plus 5 into 3. In general math you have got this one. A into B plus C. A into B plus A into C. This one you have got already. Distribution. A is distributed to B and also to C. Distributive property. So same thing here also. Distributive property also shows for this one. Same thing. Z1, Z2, Z3, Z1, Z2, Z1, anything. Z1 into Z2 plus Z3. So this one, like this one only. This one you know already. This one you got already in general maths. So same thing you have to apply here. There is nothing to learn. There is nothing new for you. No? Nothing new for you. So same thing here also. This one Z1, Z2 plus Z1, Z3. So distribution. So here complex number can be used like general maths only. The properties existence are there in complex number. If you know the associative property, commutative property, closure property of any numbers in general maths, then you will understand this one also. Identity property, this one also there in general maths. If 0 plus I 0, then identity will be this way: z plus 0 equals to 0 plus z equal to z. Same thing, a plus 0 equals to 0 plus a equals to a. 2 plus 0 equals to 0 plus 2 equals to 2. This one you got already. So this is identity property. 0 is called additive identity. 0 is, remember this, 0 is called additive identity. Additive identity. We have got additive identity in natural number. Additive identity we have got anywhere. General maths already we have learned this about additive identity. Then similarly my multiplicative identity, what? 5 into 1, 1 into 5 equals to 5. So here 1 is called multiplicative identity. Similarly here also z into 1, 1 into z equals to z into 1 equals to z. Here 1 is called multiplicative identity. Multiplicative identity. So it is like this one. This one you learned already. This one you know already. So there is nothing new here. Same thing, only this one you have to use for complex numbers. Number 8, inverse property. Inverse property means opposite sign. If z is equal to a plus ib, so minus z will be minus a minus ib. Inverse property, if z equals to a plus ib is a complex number, then minus z equals to minus a plus I minus b, minus a minus ib is also a complex number. So if opposites, if you change the sign of a complex number, after changing the sign also you will get a complex number. That is what is the meaning here. Let me tell you again, repeat. Let me repeat. If a complex number, after writing a complex number, later on if you change the sign of the same complex number, then result will be always complex number. It is not that after changing the sign this will not be a complex number. That is called inverse property. What does it mean? It means that this one and this one, if you add, what we will get? We will get 0. Z and minus z, if we add, we will get 0. It means we can write this way. Sorry. A plus ib plus minus a minus ib. What do we get? Break the bracket. So cancel. So it will be 0. Z plus minus z is always, which is the additive identity of C. C means complex number. Additive 0 is called when we add two complex number. Then we get, if we get 0, then 0 will be called additive identity. Two complex number after adding, if you get 0, both the complex number, 0 will be called identity of complex number. Minus z is called additive inverse. Listen, z is called additive identity. Minus z is called additive inverse. Here written somewhere. Here minus z is called the additive inverse or negative, same thing. So thus every complex number has its additive inverse in complex number. Every complex number, whenever you get complex number, its additive inverse will be there. If p be a complex number, p is not equal to 0, then there exists always a complex number q such that pq equals to qp equals to 1, then 1 is called multiplicative identity of C. When do we get, look here, Z1 and Z2 equals to 1, two complex number. Two complex number after multiplication, if we get 1, then 1 is called, here additive identity, here 1 is called multiplicative identity. Multiplicative identity. Since it is multiplied, since here it is added, so additive identity. So here it is called multiplicative identity. When do we get this type of answer? When do we get 1? When we get 1, in general math we have got 5 into 1, 5 is 1. 5 and 1 by 5, if we multiply, we get 1. That one you got in general math reciprocal to each other. So same thing here. If z into 1 by z equals to 1, this can be written this way, z into z inverse equals to 1. In place of z, we can write z inverse. Z into z inverse equals to 1. Or z inverse into z equals to 1. So you don't have to worry about z inverse. It is called z inverse, which is very easy. 1 by z only. Z inverse already I explained in previous video. Z inverse means 1 by z. So there is nothing to worry. If you understand this one, you can understand this one. So this is multiplicative inverse. So what is the multiplicative inverse of z? That is 1 by z. What is the multiplicative inverse of z? That is z inverse. Either you write this or this, same thing. What is the multiplicative inverse of a plus ib? That is 1 by a plus ib. Because a plus ib and 1 by a plus ib, if we multiply, you will get 1. A few of these are simply stated below. These are the formula means. So this one you can, if you cannot remember, if you do this practically, you will get this. Z1 plus Z2 whole square. So a plus b whole square formula. A square plus 2a plus b square. A minus b whole square. Z1 minus Z2. Z1 plus Z2 whole cube. A cube plus b cube formula. So this one we can, that means what is shown here, whatever formula in algebra we applied, same type of formula we can apply for complex number also. If we applied in general maths a plus b whole cube, so here we can apply z1 plus z2 whole cube also. This is what written here. Whatever formula we applied in general maths, we can apply here also. For whole square, for whole cube. Example number 1. If x plus iy plus 3 equals to y plus 4xi, then find x and y. This one is done here. Still, I will show you once. X plus iy plus 3 equals to y equals to 4xi. Here, equal sign is there. So remember, I hope you remember, the real part will be equal. Imaginary part will be equal. So let us identify the real part first. That means we have to make it a plus ib form. Real part first, imaginary part second, both sides. Then we can equate the real and imaginary part. So let us identify the real part together. X plus 3 I have written together because there is no I. Next plus iy equal y plus 4 I 4x, same thing, 4xi or I 4x, same thing, because here I is written before the letter, so let me write this one, same thing. Now equating, or you can use comparing, or comparing, you can use any word, comparing real and imaginary part, we get this. You have to write whenever this type of sum comes in exam. If you don't write this sentence, this part of sentence, then you will not get full marks. Remember that. Simply doing the sum, you may not get marks, may not get full marks. So this is you have to, it is compulsory to write. So next, already written, equating or comparing already written. So we will write x plus 3 equals to y. X plus 3 equals to y. Iy equals to I 4x. So directly we can write 4x equals to y. Look here. I have not written y equals to 4x. I have written 4x equals to y. Same thing. If I write y equals to 4x, then y will be before equal sign. But here x is before equal. So in order to make both the equations same, I have written 4x first. Because meaning is same. If 5 equals to x or x equals to 5, same thing. No? So now we will write x minus y equals to minus 3. Here we will write 4x minus y. Okay, wait. We have done already in class 9 linear equation. Na? Linear equation. Here y equals to how much? What is the value of y? 4x. So in place of y, let us write how much? 4x. Y is equal to 4x. So y in place of y, 4x. So x minus 4x equals to plus 3 goes that side, minus 3. Minus 3x equals to minus 3. Just we can cancel. X equals to 1. X equals to 3 by 3, 1. So 4 into 1 equals to y. 4 equals to y, or y equals to 4. What was the question? Find the value of x and y. We have got x and y. So other only complex number properties we have used here only. We have used complex number property at this much only. But after that we have done general maths. This part is not related with complex number property. This one we have used as linear equation in two variables. Find the additive inverse of z. Z equals to minus 4 plus 5i. We have to find out minus z. Simple. So both sides we will multiply by minus. Minus, okay, let us write this way. 4 minus 5i. Now, additive inverse of z minus 4 plus 5i we have got. Now, question is that whatever you have written, that is correct or not? The answer is finished. Find the additive inverse of z, that is 4 minus 5, answer. But whether it is correct or not, then z and minus z, if we add, we will have to get 0. So z is minus 4 plus 5i, minus z is 4 minus 5i. So this one cancel. So 0. So additive inverse means what? The sum of both the complex number must be 0. This one is verification only. This is not required for exam. This one for us, that we must be satisfied whether the sum is done which is correct or not. Example number 3. This is little important. Remember, this is important. This sum is important for your exam. For a real number alpha, beta, a and b, if alpha plus I beta whole to the power 1 by 3 equals to a plus ib, then show that alpha by a plus beta by b equals to 4a square minus b square. মোৰ ফোন নম্বৰ ক্লাছ 12 কথা কি ক'লা ক্লাছ 12 কথাটো 2 মিনিট ৰৈ দিয়াচোন হৈ যাব দিয়া হয় 2 মিনিট আহিম কিয় here written alpha plus I beta whole to the power 1 by 3 equals to a plus ib. This is given. Since this is given, so from given one we have to show alpha by a plus beta by b equals to 4a square minus b square. This is what we have to show. Now what we will do, by looking this we can understand that we have to do cubing both sides. Why cubing both sides? because here 1 by 3 is there. 2 to the power 1 by 3. If we do cubing, then 3 cancel. So in order to get 1 by 3, power is fraction. So we have to try to remove fraction from the power. That is why what is called cubing is done. Only because of that. There is no other option. Now, alpha plus I beta. 3 cancel. This one a plus b whole cube formula. A cube plus b cube plus 3a square b plus 3ab square. Formula. Alpha plus I beta equals to a cube minus ib cube. I cube is minus I, we know that. Plus I 3a square b minus I square is minus 1, so I have written directly minus 3ab square. I square is minus 1, so plus minus minus. Alpha plus I beta equals to a cube minus 3ab square. This is real part written together. Minus plus I 3a square b minus ib cube. Let us go there. Alpha plus I beta equals to a cube minus 3ab square plus I. Let us take common. 3a square b minus b cube. Just I is taken common in order to make a separation of real and imaginary part. This is real part, this is imaginary part. That is what our aim. So in between equal sign is there. In between equal sign is there. So equating. So I will not write all the sentence. So alpha is equal to a cube minus 3ab square and beta is equal to 3a square b minus b cube. Real part, real part. Imaginary part, imaginary part. That is what done, nothing new. Now what is to show? Alpha by a plus beta by b. So alpha is equal to a. Let us take common. Here beta is equal to, let us take b common. Now we can write here alpha by a equals to a square minus 3b square. Here beta by b 3a square minus b square. This one I hope you understand. A has to come here. After doing cross multiplication, we will get same thing. B has come here. This is like this. X equals to 3b. Then we can write x by 3 equals to b. I hope you understand this. This is just related to algebra. Alpha by a. Here alpha by a plus beta by b. We have got alpha by a and beta by b. In between plus sign. So we will add this. Alpha by a plus beta by b equals to a square minus 3b square plus 3a square minus b square. Just putting the value, nothing moves. So a square plus 3a square, 4a square minus 3b square minus b square, 4b square. 4 can be taken common, a square minus b square. So hence proved. Okay. Conjugate complex number. Z equal to x plus iy. So this one we know. So conjugate. Conjugate is very easy. Conjugate is related to what is called additive inverse. If z equals to x plus iy, then conjugate will be x minus iy. Look here. X plus iy is a complex number. Its conjugate will be only imaginary part will be changed. The sign of imaginary part will be changed. If z is equal to z equals to x plus iy, then its conjugate will be signed denoted this way, z bar. Z is a complex number, that is x plus iy. Z bar will be x minus iy. That much only. This much only you have to learn, nothing else. Only sign will be changed for imaginary part. Real parts sign will never change. So this is conjugate. This is called conjugate. Conjugate is denoted by Z bar. So these are here some properties. Sub property. Here if Z is a real number, Z bar equals to Z. For example, if Z equals to 5, then Z bar also 5. Look here. Z equals to 5 plus 0i. So Z bar will be 5 minus 0i. If Z is a real number, that means sorry, here equals to 5, here also equals to 5. Okay? So if Z equals to 5, Z bar also 5. This is what I have shown. So other things also you can understand yourself. Find the conjugate of 2 plus 3i, 3 minus 4i. 2 plus 3i into 3 minus 4i. So two complex numbers are there, in between multiplication sign is there. So we have to find out the conjugate of this. So first of all, this one we have to try to get in the form of a plus ib. Then only we will convert to a minus ib. First we will multiply, then we will try to get in the form. So let us multiply 2 into 3, 6, 2 into 4i, 8i, 3 into 3, 9i, plus into minus is minus, I into I square, again minus, plus, 3 4 ja 12. I hope you understand, plus into minus is minus, I into I square is again minus, so minus minus plus, 6 plus 12, 18, plus I, minus 8i plus 9i is I, 18 plus I, answer is 18 minus I. Answer is 18 minus, conjugate we have to write. So same thing here, after doing this calculation you can understand the calculation, it is very easy actually. Example number 2, find the multiplicative inverse of Z. Multiplicative inverse means, what do we understand? Z inverse. Whatever, if Z equals to 2 minus 3i it is given. We have to find out Z inverse. Z inverse means already I explained 1 by Z. 1 by Z. So we will do the calculation 1 by 2 minus 3i. So whenever we get complex number in denominator, remember that always multiply by its opposite sign. Always. Always. 2 minus 3i is there. So multiply by 2 plus 3i in numerator and denominator. Then this one we can write, if you don't remember, so let me write this way. A minus b into a plus b, a square minus b square. Here only 2 plus 3i. 2 square is 4. I square is minus 1. Minus minus plus. 3 square is 9. Here 2 plus 3i. 2 plus 3i by 13. So 2 by 13, I 3 by 13, I hope you understand. 13 is the denominator for this one and for this one also. I is taken separate, the same thing, I into 3i. Now this is the calculation of 1 by Z. 2 by 13 plus I, 3 by 13. What is this? Z inverse. Multiplicative inverse. This one Z is equal to 3 plus 4i give by 5i given. We have to find out Z into Z bar. Z into Z bar. Z is given, we will find out Z bar first, then we will multiply. Z bar means what? Z bar means we have to change the sign of imaginary part. Z bar means we will change the sign of imaginary part. So let us see Z bar. Z bar means 3 plus 4i by 5i bar. Bar. So 3 minus 4i, this is minus 5i. Think that this is 0 plus 5i. This is minus 5i. So z bar we have got, z we have got, we will multiply. Just to multiply only. Z into z bar we have to find out. So here, look here, this one you may get some difficulties, you may forget. Here z equals to 3 plus 4i by 0 plus 5i. Now z bar equals to 3 plus 4i bar 0 plus 5i bar. This one bar we can put z1 by z2. If we put bar here, we can write z1 by z2 bar this way. This is theorem already got. This is a property. So now we have to multiply z into z bar. Z is 3 plus 4i by 5i into z bar is 3 minus 4i by minus 5i. Calculation, just calculation now. 5 into 5 is 25. I into I is I square minus 1. Minus minus plus. So below 25. 3 plus 4i into 3 minus 4i. 3 square plus that a plus ib into a minus ib is equal to a square plus b square. Directly you can write. We got already. In previous video I explained already. A plus ib into a minus ib will be a square plus b square. Isn't it? Look here. A plus ib into a minus ib. That is a plus b into a minus b formula. So a plus b into a minus b what? A square minus b square. A minus a square minus b square. A means a is b. A square minus I square is minus 1. B square is b square. So a square minus minus plus b square. So whenever same type of digit plus minus, directly you can write. So 3 plus 4i into 3 minus 4i. Directly you can write 3 square plus 4 square. If you remember this one, you have to remember this one. This one already I explained in previous video. So 3 square is 9 plus 16, 25. 25 equals to 1. So z1, z into z bar is 1. You can see, you can check it back again. This is also important sum. This is important sum. For example, number 4. X plus iy equals to a minus I by a plus I. So question is that what to do? If x plus iy equals to a minus I by a plus I, then prove that x square plus y square equals to 1. So when we get x square plus y square, already just now I have explained. When we get a square plus b square, when we multiply a plus ib into a minus ib, when we will get x square plus y square, when we multiply x plus iy and x minus iy. No, then only we will get x square plus y square. So x square plus y square, when do we get? When x plus iy and x minus iy will multiply. So if we x plus iy is a minus I by a plus I. If x minus iy, then a minus I, a plus I already explained. No? So why it is written? Okay, let us write like this. X plus iy is a minus I by a plus I. X plus iy conjugate. That means what? X minus iy equals to a plus I. This will be a minus I hope instead. No? So we will multiply now. X plus iy into x minus iy equals to this one and this one written here equals to a minus I by a plus I into a plus I by a minus I equals to 1. Finished? How finished? Because x plus iy into x minus iy is x plus y square. X square plus y square. No? Exercise we will do in next video.